give the test, what's going to happen is on the end of that test. Yeah.
Materials or objects when torque is applied. This testing allows companies to make sure that products such as pharmaceutical devices, orthopedic implants, and electronic components function as intended before they are shipped out to customers. Torsion testing can be performed on both raw materials and finished products. Raw material testing is done to confirm that manufacturers are using materials that meet the performance specifications for their intended application. Finished product testing ensures that finished products perform as expected. Types of torsion testing vary from product to product, but can usually be classified as failure, proof, or functional testing. Failure testing is when a product, component, or specimen is twisted under failure. This may be a static test to determine the ultimate shear strength, or a cyclic test to determine product longevity before failure under various loading conditions. Failure can be classified as either a physical break or a yield or defect in the specimen. Proof testing is when a torsional load is applied and held for a fixed amount of time. This proves that the product can withstand torsional forces for a set duration. Functional testing is performed on finished products such as bottle caps, medical implants, and steering columns to make sure the product performs well under the torsional loads it will encounter in use. To learn more about materials testing, visit our YouTube channel and don't forget to hit subscribe.
Let us go through the theories behind the torsion test. Now, a shaft is an example. A shaft is an example of a member in torsion. Actually, we have gone through the prismatic bar for a member in bending as well as tension and compression. Here, we'll find out, we'll see that shaft is an example of member in torsion. What is shaft? This is used mostly in drilling application to transmit power from one point to another. Say motor is running, it is running running certain gearbox or certain wheel drive, and it is being this power is being transmitted by a coupling, which is nothing but a shaft. Now, so the power being transmitted from a motor to machine tool, from an engine to the rear axle of the automobile, or from steam or hydraulic turbine to an electric generator. These shafts used for the purpose may be solid or liquid. The shafts can be meant for power transmission from motor, from any other prime mover to the any other gearbox, maybe automobile differential gearbox or hydraulic turbine to electrical generator, all those things. When the shaft is made to transport a power, a pure twisting couple or torsion torque test acts about its polar axis. So what type of power is being transmitted? It is a pure twisting couple, a torque, or means two sides of two parallel forces of same magnitude, but of different different line of action. They are away by a certain known distance, is creating a torque, but they are working in opposite direction to each other, is creating a torque or couple over an axis, over about a polar axis. The shear stress are now generally set up perpendicular to the radius at all transverse section. So this, due to the action of this torque, we are producing not the longitudinal stress, but shear stress, the stresses acting parallel to the radius of all transmission track. Now, as a result, a complementary shear stresses are developed on the longitudinal planes, which causes a distortion of filament. So we have to make a complementary shear stress, means a equal and opposite shear test, right? Supposed to be developed in the longitudinal plane, which causes a distortion of the filaments. As the cross section may transverse is symmetrical, the cross section is symmetrical, say these points remain on the same radial distance before and after the twist. Points remain at the same radial distance before and after the twist. The angle of twist is reckoned over the length of the shaft. The angle of sweep is reckoned over the length of the shaft. The assumptions made in the theory of torsions are like this. The materials of the shaft is homogeneous, isotropic, and perfectly elastic. Should be homogeneous means uniform everywhere. Isotropic, they have the same property in all three directions, and they are perfectly elastic, means they will go back to their original shape when is external within when is externally applied load within a limit will remove, it will go back to the original shape. So homogeneous, isotropic, and perfectly elastic, three are the properties. The material obeys Hooke's law, means stress is here proportional to strain, and if its stress is removed, constant member will go back to the original shape and side. Stress means, and the stress will be within limit of opportunity, limit of opportunity. The twisting couples acts at the transverse plane only. Twisting couple acts at the transverse plane only. All the radii remains straight after torsion. The twisting couple with transverse plane means planes which are at normal to the longitudinal axis of the beam. All radius remain straight after torsion. The radius before the torsion will remain straight, will not bend or distort any other means. Parallel planes normal to the axis do not warp or distort after torsion. All parallel planes normal to the axis do not wrap or means will not be constrict or distort after torsion. A cross-sectional area at any axial distance, axial length rotates at a released distance at a rigid plane. That is at all diameters of the cross-section rotates to same angle. So cross-section at any axial plane end rotates at a rigid plane in any axial length. Cross-section at any axial rotates as a rigid plane, that is in all diameters of the cross-section rotate to the same angle. Now these are the assumptions of the torsion. But let us decide, let us calculate, go through the torsion equation. Now what is given here? It is a circular shaft is given of certain length is given as L and diameter is given as D. That is the diameter D. It is subjected to a torque T. It is subjected to a torque not that short. The shear strength phi of the elements at a distance r from the axis is given as at a distance r from the axis is constant for a particular value of t. The thus OA twist is to OP. This is the it is the rotation at the element of the length, where Now, let theta be the angle of twist of a cross section related to the another cross section at section L apart, which is given here. Here theta or phi. Theta. Now arc AB will be arc theta is equal to L into phi. Arc AB. This is the arc AB, which is equal to, this is also arc theta is equal to length into phi. L into phi, L, phi is equal to tau divided by G, which, as you know, the shear strength is equal to torsional strength divided by the modulus of rigidity. So tau divided by R, tau divided by G into theta by L. Now, the tangential force of the element tau is equal to 2 into pi R. Tau is equal to multiplied by 2 into pi R into dr. And tangential of the element is tau multiplied by the area, means 2 into pi R is the perimeter divided multiplied by the thickness of the ring. So this is the area of the ring. It is the tangential force acting over the area. Area multiplied by the torsion shear stress is the tangential force acting on the ring, because force acting is shear stress. So shear stress it is which acting tangential to the element. The moment of the shear force on the element. Now, if we calculate the moment, if we have to multiply the radius of the thickness. So the sum of the moment of the whole shaft, integration of tau 2 into pi R into dr into R. So sum of the whole shaft, 2 integration of t into pi R into dr into R, or integration of 0 g into theta divided by R into R, 2 into pi R into R dr into R. So g into theta 2 pi R whole square 2 pi into dr whole square and 2 pi R dr na ठीक है ऐसे 2 pi R and dr 2 pi R and dr into whole square is the polar moment of inertia of the shaft, which because polar moment of inertia it is the area multiplied by the total area is the circumferential distance multiplied by dr multiplied by the square of the distance from the center, the polar moment of inertia of the shaft, thus which is given as G into theta by J into J. So from 1 and 2 we'll say 1 and 2 together we'll have G theta by J, R by theta, T theta by L. This shows that for a given shaft, the shear stress is proportional to shear strength. This shear stress is proportional to the shear strength. Shear stress is proportional to radius. And this figure below shows the shear stress distribution in solid shaft of radius R. The similar distribution of hollow shaft analysis like R, and outer radius R theta is shown 0. Then this above equation or equation of torsion is analogous to equation for where T divided by J is corresponding to BMI, tau divided by T corresponding to sigma into R, and G corresponding to R. As the polar moment of inertia, J is equal to Ix plus Iy, then for the circular shafts, J is equal to pi by 464, in pi by 4 by 64 to d4, again the pi by 4 by 64 by d4, or for circular shaft, pi by 32 to the power 4. By solid and hollow shaft, this following direction can be made. For solid shaft, maximum shear stress, tau T divided by T d divided by 2 divided by pi to the 4 by 62, or 16T, 16 capital T divided by pi d cube for the outer shaft. And for hollow shaft, if D and D are outer and D, capital D and small d are outer and small inner diameters respectively on the hollow shaft, then J will be pi d to the power 4 minus small d to the power 4 divided by 32. Maximum stress tau T into d to the d divided by 2 divided by pi d to the power 4 minus d to the power 4 into divided by 32. and that is 16t divided by 16t into capital D divided by pi d to the power 4 minus d to the power 4 at the outer surface. Now, torsional moment of resistance of resistive torque. The maximum torque which can be obtained by which can be carried by a given section of the shaft for a given maximum value of shear stress is defined as torsional moment. So the maximum torque which can be obtained, this is the maximum torque which can be at a given section of shaft for a given maximum value of shear stress. So for where for a maximum value of shear stress, what is the maximum value of torque which is supposed to be faced by section section of shaft, which is called torsional moment of the resistance of the resisting torque or the resisting torque. It is the sum of the moments of tangential stresses acting on a transverse section. It is the sum of moment of tangential shear stress acting on a transverse section. Now, J divided by R is known as the torsional moment or polar sectional moment. The torsion torque per radian twist is known as the torsional stiffness scale. K is equal to T divided by theta is equal to J divided by J into G divided by I. The parameter J into J is known as the torsional rigidity of the shaft, similar to flexural rigidity EI of a beam. The parameter J into G into J is known as the torsional rigidity of the shaft to flexural rigidity of a parallel beam. This is the torsional rigidity of the shaft, similar to flexural rigidity EI of a beam. This equation we know G into J is equal to T divided by theta into L, theta divided by L. This torsional rigidity is also torque per unit angular twist. This is the torque per unit angular twist is also another definition known as torsional rigidity. What is the power transmission? Shafts are the medium to transmit power from the point of power generation to the point of its application. This is the shafts, and this is the medium. The power transmitted is work done per second. Work done per second. Power is transmitted. So power will be torque divided by omega. Means torque is the force which is doing per second is doing this radius of A. So omega is equal to capital T dot 2 into pi into N divided by 60 is equal to 2 into pi N T divided by 60, where T is the applied torque and N is the revolution of the shaft in RPM. A shaft can transmit power at more than one section to the different machines. Shaft may transmit power at more than one section to different machines. So the shafts may also be subject to different torques on different section. So T while we are using 2 pi N by 60, 2 pi NT by 60. That T is the applied torque and N is the RPM or revolution of the shaft part in RPM. A shaft may transmit power of more than one section to different machine. Also, the shafts may subject to different torques in different section. In such a cases, the principle of conservation energy can be applied. Usually, the torques are designed on the basis of limited value of stress and the angular deformation. So, the shafts can be subject to different torques in different section. So, principal conservation of energy can be applied here. More than a shaft can be transmitted more power at more than one section at different machine. So, actually, the shafts are designed on the basis of limiting value of stress and the angular deformation. Limiting value of stress and the angular deformation. Okay. Now we are stopping the share here, and this is the end of this class, this lab. Thank you.